Greetings. Back to Math 3B, Calculus 2. We are talking about infinite series of numbers, and we're collecting a series of, or a list of convergence and divergence tests for series. So far, we have the geometric series for convergence or divergence. We have the test for divergence, and we have the integral test. And today we're going to be talking about the comparison test. So there's two of the comparison tests. I'm going to start with an already complete list of notes to potentially go a little faster. So the first test that we have is the comparison test, or what is known as the direct comparison test if you want to do searches elsewhere. And we've got a little bit of criteria in order to use the comparison test. Please keep in mind, just back up here and taking a look at these comparison tests, you're going to always be comparing your series to another series, and that other series you're going to want to easily be able to tell the convergence or divergence of. And so that typically is going to be a P series. But in general, for both of the definitions, what's A sub n? A sub n is the series that you need to determine is convergent or divergent. And your B sub n is what you're comparing it to. So the what you're comparing it to is usually a P series test. And note, remember your P series test is your series takes the form of 1 over n to the P, and remembering that n goes from 1 to infinity, and we're looking at the P here, and if P is bigger or is bigger than 1 specifically, then it converges. And if it is smaller or equal to 1, it diverges, because remember 1 over n, the harmonic series, is a divergent series. So that's how you can make great use of the P-series test. Anyway, so here is the comparison test. So the main criteria to use the comparison test is that you're looking at positive terms, because the proof of this test involves the monotonic bounded sequence theorem. So they're using sequence of partial sums. That's the definition of a convergent series. And they're also using bounded sequences. So if your lower bound is bigger, is infinite, then your series would be infinite. So let's take a look at the criteria here for the comparison test. So suppose your series and the one that you're comparing to are series with positive terms. So the first test that you can use is if the comparison series is convergent and your series terms are smaller than or equal to the B sub n, then your series is also convergent. And if the second criteria is that if the series that you are using to compare your series to is divergent and your series terms are bigger than or equal to that comparison series, then your series is divergent, right? So over here, the criteria are if your series is less than or equal to a divergent series, excuse me, if your series is less than or equal to a convergent series, then your series converges. And if your series is bigger than or equal to a divergent, then your series is divergent. So it does make use of that monotonic boundedness theorem. So let's go over a couple of these problems and how to use the direct comparison test and make that analysis. Okay. So here, note, you're just asking, does the series converge or diverge? And usually in answering that, you have to pick a test, identify the test that you're using, and make the correct conclusion on that test. So here we go. We're going to use the direct comparison test here. And keep in mind, we're still using those basic arithmetic facts of if you've got two fractions and they both have the same numerator, the one with the bigger denominator is going to be the smaller number, right? And we're going to be using that inequality. So I liken it to an example of if I have a cookie and I offer to divide it among 3 people, and then I take that same cookie and offer to divide it among 5 people. Which group of people do you want to be in? I want to be in the group of 3, the smaller number, because then I get more cookie. It's going to be a bigger number. All right. So In example number 1, we've got the sum of 1 over n squared plus 4, and that is my series. That's the series I need to determine the convergence or divergence of. And what am I going to compare it to? We always want to compare it to a p-series that has the same uh, magnitude or the same degree in the denominator. So I look at 1 over n squared plus 4, and I don't really need the 4, so I'm going to liken and maybe compare my series to b sub n equal to 1 over n squared, because that takes the form of a p-series test. It's n to a number, and I note that my p is equal to 2. That's bigger than 1, so we know that my series is going to converge. And so if I'm going to use the direct comparison test, then I have to show that my a sub n, is less than or equal to b sub n and have my b sub n convergent, because my series needs to be smaller than a convergent in order to make a conclusion. If my b sub n were divergent, I would want to show that my a sub n was bigger than that divergence so I could make a conclusion. Okay, so I come in here and I see that a sub n is equal to 1 over n squared plus 4, and that's going to be less than the same numerator over n squared, because n squared is a smaller number than n squared plus 4, so we actually have a bigger number, and I have shown here that a sub n is less than or equal to b sub n, and because b sub n is convergent p-series, I can use the direct comparison test and make that conclusion. All right, part B. Again, my series is the sum of a sub n, and in order to pick my appropriate b sub n, I'm going to pick a b sub n that's a p-series that has the same type of degree. So I'm going to not worry about that minus 1 in the denominator. I'm going to say choose b sub n to be k over the square root of k to the 4th, because I can simplify that. Square root of k to the 4th is k squared, and k divided by k squared is 1 over k. Then I can consider my p-series b sub n equal to 1 over n, or I can go, hey, that's a harmonic series and that's divergent. So if I know that my b sub n is divergent, I'm going to go to the direct comparison test and I'm going to go, okay, if my b sub n is divergent, I have to show that my a sub n is bigger than that b sub n for all n. And n is a natural number bigger than 0. So that's how I do it. And I do see here that k over the square root of k minus 1 is bigger than or equal to k over the square root of k to the 4th. Why? Because this is a bigger denominator because we have subtracted 1, right? So that's smaller. And we do have the same numerator. So, but we can simplify that k over the square root of k to the 4th. That's equal to 1 over k, and that's b sub k. So since my a sub k is bigger than or equal to b sub k, and I know that the b sub k diverges, then I make my conclusion my a sub k also diverges by direct comparison. All right, these are going to kind of get a little bit tricky, but I can see here, this is my a sub n, and I'm going to look at a sub n equal to n minus 1 over 2n times n plus 1. That's going to equal 1 over 2 to the n times n minus 1 over n plus 1. That's certainly true because it's just equivalent. And then I can say, because that's a minus, I can say that that's well less than or equal to 1 over 2 to the n times n over n plus 1, right? Because I have a bigger numerator now and the same denominator. But this is also, I note, is less than 1. So I can say here that this is less than or equal to 1 over the 2 to the n times 1. And that is actually equal to 1 over 2 to the nth power, right? Because 1 to the nth for any n is equal to 1. So I have shown here, because of this inequality sign, that my a sub n is less than or equal to 1 over 2 to the n for all n. So if I choose this to be my b sub n, and I see that the sum of b sub n is a geometric series with absolute value of r equal to absolute value of 1/2 is less than 1 is convergent, I have in conclusion that since a sub n is less than or equal to b sub n and b sub n is a convergent geometric series, then a sub n converges by direct comparison. Good. All right. So I will skip through this here and you can take a look at this calculation. Please do, and maybe we will hold off on doing part D for the office hours because I want to move forward with the um, limit comparison test and go over that one. I do want to, I think I put something further, notes on the direct comparison test. Let's do that before we move forward. So this page should be right after the last page of direct comparison test. So to be clear, remember, if your series is smaller than a convergent series, then your series converges. And if your series is bigger than a divergent series, then your series diverges. But let's look at the opposite scenario. If your a sub n is less than or equal to a b sub n, and that b sub n is divergent, you've said nothing, okay? So there's no conclusion and you have to pick a different convergence test. So that would be the opposite of a sub n being bigger than or equal to a divergent. If a sub n is bigger than divergent, then your series diverges. But if a sub n is smaller than a divergent series, you have said nothing, okay? Also, if a sub n is bigger than a convergent series, you've also had no conclusion. So some of these examples are 1 over n is clearly bigger than or equal to 1 over n squared, because if n is bigger than 1, n squared is going to have a bigger denominator, and that's going to be a smaller number. But so we have this case scenario that we have a divergent series is bigger than or equal to a convergent series, right? But then we also have that 3n over n squared is bigger than 1 over n squared. So here's an example where I can find series that are divergent that are bigger than 1 over n squared, and I can also find convergent series that are bigger than a convergent. So there's convergent and divergent series bigger than a convergent series. So you've really said nothing. Good. And there's similar scenarios to that. So please read through those. So let's get back to the limit comparison test. And sometimes when you can't really use the direct comparison test because you can't make that a sub n less than b sub n, or you can't make that a sub n bigger than a b sub n, so you can't really make a conclusion because it's easy to find the convergence or divergence of b sub n, but it's kind of hard to make the bigger than or less than calculation. So when that happens, you might want to try the limit comparison test. And when do you usually want to use the limit comparison test? When you have rational expressions. So if you have a polynomial divided by a polynomial, you'll want to use the limit comparison test. Or if you have a radical expression, you might want to use the, of like a ratio of radical terms, you might want to use the limit comparison test as well, because you would pick your comparison series in the same way that you used to do the direct comparison. All right, so let's read the test. Here, suppose a sub n and b sub n are series with positive terms again. If the limit of the quotient of a sub n divided by b sub n goes to a limit that's not equal to 0, and that c is bigger than 0, well, of course it would be because you have a series of positive terms, then either both the series converge or both diverge. Good. And I just want to point out that you can still stay within the test if you have this following criteria. So let's suppose that the limit does equal 0. Well, if the limit does equal, the limit of that a sub n divided by b sub n does equal 0, note that 0 is a finite limit and it's a limit that does exist. So if that limit still exists, but it's actually equal to 0 and not a non-zero number, you can still stay within the test provided that b sub n converges. Then you can say that a sub n converges. Please note here in purple, if the limit is equal to 0 and b sub n diverges, you don't have a conclusion and you have to pick a different test. The second part of the corollary, and just think of this as, what if the limit of the quotient is infinite or does not exist? Then think of that as divergent and go, okay, if I end up with an infinite limit, but I'm actually comparing to a divergent series, then my series is also going to diverge. So it's still that they either A and B both converge or they both diverge. And also note in purple here, if that limit of the quotient does not exist and b sub n converges, then you have that opposite scenario and you can't make a conclusion and you have to pick a different test. Okay. So again, I remind you, when is it a good time to pick a comparison test? Because keep in mind now we've got more than one test, and it might be like the limits of or calculations of integrals. Which method am I going to use? So which convergence test am I going to use? Am I going to use geometric series? Am I going to use p-series? Am I going to use the integral test? Am I going to use comparison tests? So you want to kind of use the comparison test when you have a rational expression or a radical expression, as I mentioned, and when it's pretty much hard to do the direct comparison, because sometimes direct comparison is the easier way to go. Good. So let's go over this one, and maybe we can use the one earlier in class. So here I've got a radical expression. I've got k over the square root of k to the fourth plus k minus 1. And I want to limit compare it with something that has similar degree. So I'm going to remove the k's and the k minus 1 and just go for the highest power over the highest power. And so I have the highest power in the numerator is k, and the highest power in the denominator is square root of k to the fourth. So that simplifies to 1 over k, and I'm going to consider my b sub n to be 1 over k, and I know easily that that is divergent by either it's a harmonic series or it's divergent by p-series. So here I go taking the test. So here I've identified my comparison, and now I'm just going to take that quotient. So I first put my a sub n, which is n over square root of n to the fourth plus n minus 1, and I'm dividing it by 1 over n. Division by a fraction is multiplication by the reciprocal, and now I'm just going to be taking the limit as n goes to infinity of n squared over the square root of n to the fourth plus n minus 1. So that does go to infinity over infinity, but I would not use L'Hopital's rule in calculating that limit. I would factor out the highest power of n, and the highest power in the numerator and the denominator is actually n squared. So in order to pull n squared out of that radical, I need to factor out n to the fourth. So that's what I do here underneath the radical first. And then I do know that in order to pull that out, the square root of n to the fourth is going to be n squared, right? So this is actually equal to n squared, and you are going to be able to cancel it. Now I'm going to use my limit of composition of functions and sums, and my limit laws. 1 is a constant, it's going to go to 1. 1's going to go to 1 down here. 1 over n cubed is going to 1 over infinity, which is going to 0. And 1 over n to the fourth is going to 1 over infinity. That's also going to 0. So my full limit is going to 1 over the square root of 1 plus 0 minus 0, and that's going to 1. That is my c, and I know that now my limit as n goes to infinity of a sub n over b sub n is going to equal 1, which is not equal to 0, and the sum of b sub n equal to 1 over n diverges, then my conclusion is my series diverges by the limit comparison test, and that is what that equals. Good. that's kind of a fun test to use, and it's a bit easier in many cases than the direct comparison test. So I'm going to let you read the rest of these. I did go over that one as well, so I do think I completed the entire section here. I hope to see you guys in office hours. Take care.